Welcome to this comprehensive guide on C-sharp file operations designed for beginners. Understanding file interaction is a fundamental skill for any C-sharp developer. It enables applications to store and retrieve data persistently, ensuring information is not lost. We will explore core concepts and practical examples to master file handling, providing foundational knowledge for robust applications. File input-output, or I/O, refers to processes an application uses to read and write data to external storage, such as hard drives or network locations. This is crucial for tasks like saving user preferences, logging events, managing application configuration, and processing large data sets. Without effective file I/O, applications cannot store information beyond their current runtime session. In C#, all file and stream operations are primarily handled within the system.io namespace. This foundational namespace provides a rich set of classes for efficient file system interaction. These classes allow you to create, delete, and manage directories, interact directly with individual files, and handle various types of data streams. It is the central hub for C# file manipulation. The system.io namespace contains essential classes like file, directory, stream reader, stream writer, and file stream. Each serves a specific purpose in managing file system interactions. File is for simple operations, directory for managing folders, stream reader for reading text, stream writer for writing text, and file stream for low-level, byte-oriented file access. Understanding each is vital for effective C# file handling. For simple, quick file operations, the static file class is incredibly useful. As it's static, you directly call its methods without instantiating an object. It provides straightforward methods for tasks like checking if a file exists using file exists, reading all text content into a single string with file.readAllText, or writing an entire string to a file using file.writeAllText. This class is perfect for quick utility functions where fine-grained control isn't needed. For granular control over file access, especially with larger files, binary data, or specific read/write permissions, FileStream is the go-to class. It operates at a lower level, directly working with sequences of bytes. This allows fine-tuned control over how data is read from or written to the physical file, including seeking to specific positions. FileStream is suitable for complex scenarios where performance and exact data manipulation are critical. To create or open a file with FileStream, you specify the file path, a file mode, and file access. These parameters ensure the file stream is configured precisely for your intended operation. It is crucial to always close a file stream instance after operations. Failing to properly close can lead to file locking issues, data corruption if buffered writes are not flushed, or memory leaks. Explicitly calling close ensures proper resource release and data integrity. However, the using statement offers an even safer approach. StreamWriter is a powerful class designed for writing character-based data, like strings, to an underlying stream. It acts as an adapter, efficiently translating characters into bytes using a specified encoding. The underlying stream, commonly a file stream, then writes these bytes to the physical file. This makes StreamWriter indispensable for creating and modifying text files, log files, or any textual content. With StreamWriter, you have flexible options for writing text. The write method appends text without line breaks. The writeLine method is useful for writing entire lines, as it automatically appends a new line character after the text. This ensures subsequent writes start on a fresh line, making output well-formatted and readable. The distinction is important for precise text formatting. A critical best practice for robust resource management and C# file operations is to always employ the using statement. This powerful construct ensures StreamWriter and its underlying file stream are automatically closed and disposed of, releasing all resources, even if an exception occurs within the block. It effectively replaces explicit close calls and try-finally blocks, making your code cleaner and more reliable by guaranteeing resource cleanup. Similarly to StreamWriter, StreamReader serves as its essential counterpart, designed for reading character-based data from an underlying stream. It's perfect for consuming and parsing text files created by StreamWriter, manually edited, or generated by other applications. StreamReader efficiently translates bytes from the stream back into characters, allowing your application to easily process human-readable text content from files. It simplifies extracting information from text-based data sources. One of the most common and efficient ways to read text files with StreamReader is line by line using the readLine method. This method reads all characters up to the next new line and returns them as a string. When the end of the stream is reached, readLine returns null, signaling loop termination. This approach is ideal for structured text files like CSVs or logs, allowing sequential processing without loading the entire file into memory. Alternatively, to read the entire content of a file into a single string, the read-to-end method is an excellent option. This method reads all characters from the current position to the end of the stream and returns them as one large string. While convenient for quick access, it loads the entire file's content into memory. Therefore, read-to-end is best suited for smaller files where memory usage isn't a significant concern. For very large files, reading line by line is more memory efficient. Just like StreamWriter, StreamReader also benefits immensely from the using statement for robust resource management. Employing a using block with StreamReader guarantees automatic resource disposal, ensuring the underlying file handle is properly released and the stream is closed, even if an error occurs during reading. This practice is fundamental for preventing file locking issues and avoiding memory leaks, contributing to stable and efficient applications. Always wrap your StreamReader instances in a using statement. Now, let's combine what we've learned into a complete, practical example. This demonstration will illustrate the full life cycle of a typical text file operation in C#. First, we'll programmatically create a new file. Then, we will write sample textual data to this file using StreamWriter. Finally, we'll read that same data back using StreamReader. This end-to-end example will solidify your understanding of how these core components work in harmony to manage persistent data. First, we define our file path and the content to write. It's highly recommended to use path, combined when constructing file paths. This method intelligently handles path separators, such as backslashes on Windows and forward slashes on Unix-like systems, ensuring your application creates platform-independent file paths. This prevents common path-related errors and makes your code more portable. Next, we use a StreamWriter within a using block to write our content to the specified file. This using statement is vital as it guarantees our content is written to the file, creating it if it doesn't exist or overwriting it. More importantly, it ensures StreamWriter and its underlying file stream are automatically closed and disposed of, releasing all system resources, even if an exception occurs. This robust pattern prevents resource leaks and file locking issues. After writing, we'll use a StreamReader in another using block to read the data back from the same file. We'll demonstrate reading the file line by line using a loop and the readLine method, printing each retrieved line directly to the console. This allows us to visually verify that the write operation was successful and that the data was preserved and accurately read back by our application. This complete example demonstrates the fundamental workflow for text-based file operations in C#. It illustrates the entire process, from writing data into a file using StreamWriter with proper resource management via the using statement, to the subsequent retrieval and reading of that data using StreamReader. This full cycle showcases how these core classes work together seamlessly to manage persistent data storage, providing a clear blueprint for your own file handling tasks. A crucial tip in file operations is the necessity of always closing your streams and disposing of related resources. Failing to properly close streams can lead to file locking issues, preventing other applications from accessing the file, potential data corruption if buffered writes are not flushed, or even memory leaks. This is precisely why the using statement is your best friend, as it automates this critical cleanup process, guaranteeing resource release even if errors occur. For robust applications, consider implementing try-catch finally blocks for thorough error handling. This is especially critical when dealing with file operations, which are susceptible to various failures. These failures can stem from issues like insufficient user permissions, attempts to access non-existent file paths, or other general I/O exceptions such as a disk being full. Proper error handling ensures your application can gracefully recover, log the error, or inform the user of the issue. Always use the path. combine method when constructing file paths to ensure your application works correctly across different operating systems. This method intelligently handles path separators. For instance, Windows uses backslashes, while Unix-like systems use forward slashes. Path combine abstracts away these platform-specific details, ensuring your application generates correctly formatted and functional file paths regardless of the environment, making your code more portable and robust. Remember to catch and handle potential exceptions common in file operations. These include file not found exception, thrown if your application attempts to access a non-existent file, and unauthorized access exception, which occurs if your application lacks necessary operating system permissions to read, write, or create a file or directory. By specifically addressing these anticipated exceptions, you make your file operations significantly more resilient and user-friendly. By mastering Stream Reader, Stream Writer, and FileStream, you will equip yourself with powerful tools for efficiently managing data persistence in your C# applications. These three classes form the fundamental backbone of text and binary file handling in the .NET ecosystem. Consistent practice with these concepts, through building small projects and experimenting, will solidify your understanding and proficiency, enabling you to build more capable and data-driven applications. Thank you for watching this comprehensive tutorial on C# file operations. We hope you found it informative and helpful, providing a solid foundation in file handling. Now, armed with this essential knowledge, we encourage you to keep exploring the vast capabilities of C# and continue building amazing, data-driven applications. Happy coding!